Hello everybody. So today we're going to complete studying vectors. Studying vectors.
So I have two-dimensional vectors right over here, vector A and vector B. And what I want to think about is how can we define, or what would be a reasonable way to define, the sum of vector A plus vector B? Well, one thing that might jump at your mind is, look, well, each of these are two-dimensional. They both have two components. Why don't we just add the corresponding components? So for this sum, why don't we make the first component of the sum just the sum of the first two components of these two vectors? So why don't we just make it 6 plus negative 4? Well, 6 plus negative 4 is equal to 2. And why don't we just make the second component the sum of the two second components? So negative 2 plus 4 is also equal to 2. So we start with two-dimensional vectors. You add them together, you get another two-dimensional vectors. If you think about it in terms of real coordinate spaces, both of these are members of R2. I'll write this down here just so we get used to the notation. So vector A, and vector B are both members of R2. Which is just another way of saying that these are both two tuples. They're both two-dimensional vectors right over here. Now this might make sense just looking at how we represented it, but how does this actually make visual or conceptual sense? And to do that, let's actually plot these vectors. Let's try to represent these vectors in some way. Let's try to visualize them. So vector A, we could visualize. This tells us how far this vector moves in each of these directions, horizontal direction and vertical direction. So if we put I guess you could say the tail of the vector at the origin. Remember, we don't have to put the tail at the origin, but that might make it a little bit easier for us to draw it. We'll go 6 in the horizontal direction, 1, 2, 3, 4, 5, 6, and then negative 2 in the vertical, so negative 2. So vector A could look like this. Vector A looks like that. And once again, the important thing is the magnitude and the direction. The magnitude is represented by the length of this vector, and the direction is the direction that is pointed in. And also, just to emphasize, I could have drawn vector A like that, or I could have put it over here. These are all equivalent vectors. These are all equal to vector A. All I really care about is the magnitude and the direction. So with that in mind, let's also draw vector B. Vector B in the horizontal direction goes negative 4, 1, 2, 3, 4. And in the vertical direction goes 4, 1, 2, 3, 4. So its tail, if we start at the origin, if its tail is at the origin, its head would be at 4, it would be at negative 4, 4. So let me draw that just like that.
I think there's a problem with the video, so let's try that again.
So that right over here is vector B. And once again, vector B, we could draw it like that, or we could draw it. So let me copy, let me paste it. So this would also be another way to draw vector B. This would also be another way to draw vector B. Once again, what I really care about is its magnitude and its direction. All of these green vectors have the same magnitude. They all have the same length, and they all have the same direction. So how does the way that I drew vector A and B gel with what its sum is? So let me draw its sum like this. Let me draw its sum in this blue color. So the sum, based on this definition we just used of vector addition, would be 2, 2. So 2, 2. So it would look like this. So how does this make sense? That the sum, that this purple vector plus this green vector is somehow going to be equal to this blue vector. I encourage you to pause the video and think about if that even makes sense. Well, one way to think about it is this first purple vector, it shifts us this much. It takes us from this point to that point. And so if we were to add it, let's start at this point and put the green vector's tail right there and see where it ends up putting us. So the green vector we've already have a version. So once again, we start the origin, the vector A takes us there. Now let's start over there with the green vector and see where green vector takes us. And this makes sense. Vector A plus vector B. Put the tail of vector B at the head of vector A. So if you were to start at the origin, vector A takes you there. Then if you add on what vector B takes you, it takes you right over there. So relative to the origin, how much did you, I guess you could say, shift? And once again, vectors don't only apply to things like displacement. It can apply to velocity, it can apply to actual acceleration, it can apply to a whole series of things. But when you visualize it this way, you see that it does make complete sense. This blue vector, the sum of the two, is what results where you start with vector A, at that point right over there, vector A takes you there. Then you take vector B's tail, start over there, and it takes you to the tip of the sum. Now, one question you might be having is, well, vector A plus vector B is this, but what is vector B? What is vector B plus vector A? Plus vector A. Does this still work? Well, based on the definition we had, where you add the corresponding components, you're still going to get the same sum vector, so it should come out the same. So this will just be negative 4 plus 6 is 2. 4 plus negative 2 is 2. But does that make visual sense? So if we start with vector B, so let's say you start right over here, vector B takes you right over there. And then if you were to go there and you were to start with vector A, so let's do that. So actually let me make this a little bit. Let me start with a new vector B. So let's say that that's our vector B right over there. And then let me give this a place where I'll have some space to work with. So if let's say that's my vector B right over there. And then let me get a copy of the vector A. That's a good one. So copy, and let me paste it. So I could put vector A's tail at the tip of vector B, and then it'll take me right over there. So if I start here, if I start right over here, vector B takes me there, and now I'm adding to that vector A, which will take me, starting here will take me there. And so from my original starting position, I have gone this far. Now what is this vector? Well, this is exactly the vector 2, 2. Or another way of thinking about it, this vector shifts you 2 in the horizontal direction and 2 in the vertical direction. So either way, you're going to get the same result, and that should hopefully make visual or conceptual sense as well. Let's say that I have the vector, actually let me give it the vector A. So we could draw it right over here. So it's equal to 2, 1. So in the horizontal, if we were to start at the origin, we would move 2 in the horizontal direction and 1 in the vertical direction. So we would end up right over here. Now what I want to do is think about how we can define multiplying this vector by a scalar. So for example, if I were to say 3 times the vector A, which is the same thing as saying 3 times 2, 1. So 3 is just a number. One way to think about a scalar quantity, it is just a number, versus a vector. This is giving you how much you're moving in the various directions right over here. It's giving you both a magnitude, and a direction, while this is just a plain number right over here. But how would we define multiplying 3 times this vector right over here? Well, one reasonable thing that might jump out at you is, well, why don't we just multiply the 3 times each of these components? So this could be equal to, so we have 2 and 1, and we're going to multiply each of these times 3. So 3 times 2 and 3 times 1, and then the resulting vector is still going to be a two-dimensional vector, and it's going to be the two-dimensional vector 6, 3. Now I encourage you to get some graph paper out and to actually plot this vector and think about how it relates to this vector right over here. So let me do that. So the vector 6, 3, if we started at the origin, we would move 6 in the horizontal direction, 1, 2, 3, 4, 5, 6, and 3 in the vertical, 1, 2, 3. So it gets us right over there. So it would look like this. So what just happened to this vector? Well, notice, one way to think about it is what's changed and what has not changed about this vector. Well, what's not changed is still pointing in the same direction. So this right over here has the same direction. Multiplying by the scalar, at least the way we defined it, did not change the direction that my vector is going in. Or at least in this case it didn't. But it did change its magnitude. Its magnitude is now 3 times longer, which makes sense because we multiplied it by 3. One way to think about it is we scaled it up by 3. The scalar scaled up the vector. That might make sense, or it might give an intuition of where that word scalar came from. The scalar can, when you multiply it, it scales up a vector. It increased its magnitude by 3 without changing its direction. But let's do something interesting. Let's multiply our vector A. Let's now multiply it by a negative number. Let's actually just multiply it by -1, just for simplicity. So let's just multiply -1 times A. Well, using the convention that we just came up with, we would multiply each of the components by -1. So 2 times -1 is -2, and 1 times -1 is -1. So now, -1 times A is going to be -2, -1. So if we started at the origin, we would move in the horizontal direction -2 and in the vertical direction -1. So now what happened to the vector? Now what happened to the vector when I did that? Well, now it flipped its direction. Multiplying it by this -1, it flipped its direction. Its magnitude actually has not changed, but its direction is now in the exact opposite direction, which makes sense that multiplying by a negative number would do that. In fact, when we just dealt with the traditional number line, that's what happened. If you took 5 times -1, well, now you're going in the other direction. You're at -5. You're 5 to the left of 0. So it makes sense that this would flip its direction. So you could imagine if you were to take something like -2 times your vector A, -2 times your vector A, and I encourage you to pause this video and try this on your own, what would this give and what would be the resulting visualization of the vector? Well, let's see, this would be equal to -2 times 2 is -4, -2 times 1 is -2. So this vector, if you were to start at the origin, remember you don't have to start at the origin, but if you were, it would be, so you'd go 0, 1, 2, 3, 4, 1, 2. It looks just like this. It looks just like this. And so just to remind ourselves, our original vector A looked like this. Our original vector A looked like this. 2, 1 looks like this. And then when you multiply it by -2, you get a vector that looks like this. You get a vector that looks like this. Let me draw it like this. And I'm purposely not having them all start at the origin because they don't have to all start at the origin. But you get a vector that looks like this. That looks like this. So what's the difference between A and -2 times A? Well, the negative flipped it over, and then the 2 flipped it over, and now it has twice the magnitude, but because of the negative, it has twice the magnitude in the other direction.
In the last video, I was a little formal in defining what Rn is and what a vector is and what vector addition or scalar multiplication is. In this video, I want to kind of go back to basics and just give you a lot of examples and give you R and how we operate with them. So let me define a couple of vectors here. So I'm going to do, most of my vectors I'm going to do in this video are going to be in R2, and that's because they're easy to draw. R2, remember, R2 was a set of all 2 tuples, ordered 2 tuples, where each of the numbers, so you could. In the last video, I was a little formal in defining what Rn is and what a vector is, and sense for what vectors are and how we operate with them. So let me define a couple of vectors here. So and I'm going to do, most of my vectors I'm going to do in this video are going to be in R2. And that's because they're easy to draw. R2, remember, R2 was a set of all two tuples, ordered, 2.
Let's try to solve the things without studying it. We'll just see this. We're just gonna skim this.
This is the point 2, 4. Or if we're thinking in position vectors, we could say that point is represented by the vector. That point is represented by the vector. That point is represented by the corresponding point times. This is very general. This worked well in R2. So in R2, this was great. I mean, we just have to worry about x's and
tried it on the iPad for a second. I'll show you my thought process. So I have root of 6 squared plus 3 squared, which is gonna be that's 36, and that's 9. So 6.7. So we want to scale it by that number, so that it's 1. Okay, so we'll just, so that's the thought process behind it. So we're going to say it is 6 over square root of same thing goes for 3 over root 6 . Okay, we got it. So we need to choose the unit vector. So this is 2, 2, which means we need the square root of negative 2 squared. It doesn't really matter if it's negative or positive, but just doing it for clarity, okay, and negative 2 power 2. Okay, this calculator is not good, so we're going to use our own calculator. So Google calculator. So we've got square root of 2 power 2 plus 2 power 2. Let's run this number. Oh, I should have. So we should, it's 4 plus 4, so we should have this one here. Okay, next question. Find the unit vector. So we're going to have square root 2 squared plus 7 squared 7 over square root of 2 power 2 plus 7 power 2. Okay, so we've done that. Adding vectors. Let's go. So we need to describe the relationship between the vectors. So it's A, it's B, it's A plus B equals 2. So 3 plus 1 is 4. 5, that's negative 1. That's the component. Okay. So we need first, let's find the sum. 5 plus 1 is 6. 6 and 2. Okay. So let us search about this parallelogram rule or something. So it's 5 and negative 5, negative 2, and it is 1 and 4. So this is pretty wrong. So how do we So I need to read this article real quick.
So we have two vectors here, vector A and vector B. And what we're going to do in this video is think about what it means to add vectors. So for example, all right, if we want to start at the head of sum, then add vector A to that. So I'll start with the tail of vector B, and then at the head of vector B, I'm going to put the tail of vector A.
Okay, now I understand it. So pretty much we want, you set this, let's set this again. So we want negative, mean 5 and negative 2, 5 and negative 2. 1 and 4. 1 and 4. So that's like the first thing. Second thing is we want it, so we want so that's cool. So that's the first part, and the second part is, so that is the -5 and -2, the 5 and -2, and then we want 1 and 4. So we want it in component form, okay? Google Calculator. So we're going to say 316, I mean 320. Okay, no, that's not what we need. So we want the sine for the y and the cosine for the x, and multiply it by 5. So 5 by sine of 320. See if this rule is correct. So it's negative 2. So let's open a text document. Text edit. So that's the first thing. Need text edit. Plain text. So we're going to copy this one. So that is y1. And we're going to change that to 5 by cosine of 320 for y2 equals 4 by 200 sine 250, 4 by sine sine 250, which is this number. Four by cosine 320, 3.16. Okay. So we need to add y1 and y2. Okay, so it's negative 2.14, negative 2.14 plus negative 3.88, negative 3.88, negative 6.02, it's negative 6.02, negative 6.02, 4.5 plus 3.6, 4.5, 4.5 plus 3.6, 8.1. What did that happen? Okay, let's try this calculator here. So there's a problem here. Changing polar form to Cartesian. Don't remember the formula. So I did it right. I don't know why did this happen. So maybe Google Calculators is not good. So we'll write so we want, oh, it used radians. Okay, that's good. Okay, so we're going to say 5 by cosine 320 plus 4 by cosine 250. So it's 2.46. 2.46. It's 5 by sine 320 plus 4 by sine 250. Negative 6.97. Negative 6.97. Okay, so there was a problem. So we're going with 8 by cosine of 30 plus 8 by, 5 by cosine 160. That's 2.22. Then we do the same thing but with sine. So 8 by sine 30 plus 5 by sine 160. 5.71. Okay. Find the component form of v plus w. Let's show the calculator. So we need 5 by cosine 170 plus 6 by cosine 260. Negative 5. Negative 5.96. And we do the same thing here. Okay, so one with AC. So we do 5 by sine 170 plus 6 sine 460. Yeah. So 5 by sine 170. This calculator is not good at all, but it's what we'll work with. 5 by sine 170 and 6 by sine 260. Negative 5.04. Negative 5.4. Check it. And show your calculator. So we want 7 by cosine 170 plus 4 by cosine 30. Negative 3.4. Negative 3.42. Now we AC that and say 7 by sine 170 plus 4 by sine 30. 3.21. Okay, show summary. So we're done today. So there were some problems with the calculators and stuff, but goodbye, have a good day.